let's get a little bit technical, all right? Hi everyone, my name is Yilong, and I'm the CEO of MegaETH. Today I would like to share with you some of the performance-related works I've been doing at MegaETH. And in particular, I would like to give you a quick overview of the current performance of Ethereum execution layer. And then I would like to share some thoughts on where we think this is going in the future. So at MegaETH, we're working on techniques to accelerate Ethereum performance at layer 2. So which means a lot of work focusing on improving the execution client. That would be Geth, Red, Aragon. However, it's impossible to design truly high-performance systems without first understanding the state of the art. Unfortunately, we couldn't find any good performance data that are up to date. So I think this also explains why the limitations of the existing system are often poorly understood outside perhaps the core dev team. As a result, we decided to take a rigorous approach to performance engineering from the beginning. And this approach is called measure then build. So following this approach basically has two steps. First, we perform really deep performance measurements of the existing system to understand their real problems. And then second, we can try to design new techniques to address these new problems. So this talk will be structured in two parts. In part one, I want to share some interesting lessons we learned from profiling the REST execution client. And I'll try to answer questions like what are the bottlenecks of the existing execution client and how do they change under different environments. And then in part two, I would like to share some thoughts on how we can improve the performance at L2 and how much performance we can actually squeeze out of it eventually. Due to the time limit, this talk will be focusing on part one. So before diving into numbers, let's do a quick, let's review some basic knowledge. So an execution client basically has two major tasks, execution and Merkelization. Execution means executing the transactions and updating the blockchain state. And Merkelization is basically computing or updating the state root after state changes. In REST, there are actually two sync modes that differ in how often they update the state roots. One is historical sync, which is used to sync from the genesis block. And in this mode, REST will compute the state root only after processing a large batch of blocks. So it's updating the state root very infrequently. And then there's a second mode called live sync, which is used to keep up with the tip of the chain. And in this case, the state root is updated after each block. So our test server is pretty powerful. It has 500 gigabytes RAM and has a pretty fast NVMe SSD. The CPU core counts doesn't really matter here because most of the works will be single threaded. And in order to simulate machines with different memory sizes, we use the Linux cgroup command to control how much memory will be available to the REST process. We run a lot of experiments. So we run both historical sync and we run live sync, and we run them under different memory limits. The idea is that this allows us to study the limiting factors of different modes and under different and how they change under different conditions. Okay, so let's talk about execution first, and then Merkelization. So this is our first experiment. We run the historical sync with all 500 gigabytes memory. And we persist our changes only every 500,000 blocks. And this figure shows the execution throughput measured in TPS as a function of block height. So the red dots are real-time TPS, and the red curve is the moving average. If we focus, and by the way, it took us 24 hours to sync from the genesis block to the tip, which is about 18 million blocks. And then if we focus just on the last 1 million blocks, we can see that REST can actually process transactions with 14,000 TPS, which is quite impressive. And by the way, this is all single thread performance because REST doesn't have parallel EVM yet. If we measure the performance in gas per second instead, we can see that also for the last 1 million blocks, REST can process, can achieve 1,000 to 2,000 million gas per second. Okay, so we know that, well, the REST's performance is pretty good, at least when the state fits in memory. But what if the state doesn't fit in memory? How much RAM do you actually need to run transactions in memory? So this screenshot shows a summary of the database tables in a fully synced REST archive. I know it's maybe a little bit hard to read from there. So I would just say it. So if we look at the bottom, we see that the total disk footprint is 2.3 terabytes. But fortunately, for executing transactions, we only need like 100 gigabytes data. These are called the plain state in REST. And by the way, it's worth noting that the MPT size, the MPT will take another 126 gigabytes. So this figure shows the time breakdown of historical sync. If we look at the red component, we can see that, so the red component is executing transaction, and the others are reading from database, verifying the execution receipts, writing to the database, and the other half, and some other steps. So if we look at the red component, we can actually confirm that executing transactions is indeed the bottleneck of historical sync. Right now, it's taking almost 2/3 of the total sync time, and I'm pretty sure there are a lot of low-hanging fruits who can to optimize the other parts even further. So making the percentage of executing transactions even higher. Okay, so why is executing transactions taking so much time? To answer this question, we instrument the REPN interpreter used by REST to collect very detailed performance metrics of each opcode. So and then we generate this opcode cost table. It contains a lot of interesting information, but it's not meant to be read on stage. I'll just quickly walk through the high-level information. So each row in this table is an opcode, and each column is a different metric. So for each opcode, we have the total count during the historical sync. We also measure the time spent on each opcode, measured in seconds. And also we can compute, and also the time percentage, and the time measured as a percentage of the total time. By the way, we ordered these opcodes in descending order of their time consumption. And then based on that, we can compute the cumulative time percentage of the top K opcodes. We can also compute the average cost per invocation measured in nanosecond. And then finally, we also show the category of the opcode in this table. So based on this table, we can graph the top 30 most time-consuming opcodes. The x-axis is the opcode, and then the blue bar, each blue bar, shows the percentage of time spent on an opcode, and the value can be read on the y-axis on the left. And then the red curve shows the cumulative percentage of time, and the value can be read from the y-axis on the right. So this graph shows that 90% of the time, execution time, is spent on just the top 30 opcodes. And second, the top 5 opcodes here are static call, keycheck 256, sload, call, and push one. So we can see that when the state fits in memory, sload is only taking like less than 9% of the total time, meaning that state access is not a bottleneck here. In this case, it's purely compute bound. So we can also group opcodes by their category to provide an alternative view. So this pie chart shows the time breakdown by opcode category. There are a few interesting things here. So first of all, on the left-hand side of this chart, we have the system and host opcodes. So they take more than 50% of the time. To explain a little bit, host opcodes are basically used by EVM to interact with its surrounding environment. So basically reading and writing storage, outputting the log records, and so on and so forth. And the system opcode is basically key check 256 plus a few other functions. So these are the more complicated functions that are implemented directly in the native language of the execution client. So in this case, we're profiling the rest of the language will be Rust. And then the stack-related operations like stack, push, pop are taking another 29% of the time. And the rest, 20% of the time, are spread across operations like arithmetic, bitwise operation, and so on and so forth. So actually, an interesting conclusion we can make here is that if we had say a JIT EVM compiler, it can only achieve at most 2x speed up on the historical workload. The reason is that the EVM compiler can only accelerate the components on the right-hand side of this pie chart. So less than 2x speed up. Okay, now that we have a pretty good understanding of the execution performance in a CPU-bound setting, let's switch gear a little bit and talk about the impact of memory. So it's no secret that REST can run pretty fast when it has a lot of memory to spare. But what happens when there's just not enough memory to hold the entire state? Well, the folklore says the performance will suffer. But is it true? Let's find out. So to understand the memory impact, we rerun the historical sync experiments under different memory limits. So ranging from 8 gigabytes, 16 to 512 gigabytes. And in addition, so basically we're using the Linux C group I mentioned earlier, this command to control the memory available. And then in addition, we reduce the disk flush period from 500,000 to 1,000 blocks. And this value, so that the experiments can actually finish without running out of memory. And this value of 1,000 is chosen carefully. And fortunately, the result is a very pleasant surprise. So this graph shows the performance of the historical sync of the last 1 million blocks as a function of memory limit. And the blue curve on top shows the total time, is the total sync time. And by comparing the data points at 8 gigabytes and 512 gigabytes, we see that the slowdown is actually less than 2x, meaning that even with just 8 gigabytes memory, REST can actually process 7,000 to 8,000 transactions per second for the latest million blocks with no problem. So to understand why, I also put 3 other curves in this graph. They will help explain this behavior. So from top to bottom, first I have the orange curve. The orange curve shows the time spent on executing transactions. And then we have so it's totally a portion of the total sync time. And then we have the green curve below, which is the time spent on loading data from the underlying database into Redis cache layer. So, so it's also strictly a portion of the execution time. And finally, at the bottom, we have this flat red curve that shows the cost of writing state changes back to the database. So if we just look at the shapes of these curves, we can conclude that the reason when we go from 8 gigabytes to 512 gigabytes, the total sync time drops purely because the execution time drops, which is the orange curve. And the execution time drops purely because the cache miss penalty drops, which is the green curve. But the next question would be, why do random disk I/O only incurs an overall slowdown of less than 2x? So it turns out this is because today's Ethereum workload has very strong temporal locality, meaning that data that are accessed recently are very likely to be accessed again in the future. So this figure shows a 2-level cache architecture currently employed by REST. So when the EVM tries to access some data, it first looks into REST's own cache. And then couldn't find the data there, REST will consult the underlying database and try to load the data into its cache layer. And then the database layer usually also has its own cache layer. And in this case, Reth is currently using NDBX database. So NDBX currently relies on the OS, simply relies on the operating system's page cache. So we measure the miss ratio of these two-level caches, and we realize that the miss ratios are only 21% and 31% respectively. So as a result, only like less than 6.5% of the requests actually hit the disks. And the average miss penalty is around 80 microseconds, basically the disk read latency. Okay, so we've been studying execution performance. It's now to also include Merkelization. Now, this is the TPS number, TPS graph I showed you earlier for historical sync for the last 1 million blocks, and Rest can do 14,000 TPS. And this is what happened if you need to update your state group after each block. Now the TPS drops to 1,000. So live sync is actually 14 times slower, even in a purely memory setting. There are two factors that can explain this behavior. The first one is Merkelization. You need to update your state group after each block, and that alone incurs a 9.3x slowdown. And then on top of that, you also, in live sync, you also write back your state changes to the database after each block. So more frequent disk flushes incurs an additional 1.5x slowdown on top of that. Why is Merkelization so slow? It turns out that updating the state requires a lot of tree traversal, which translates to a lot of database read operations. And even though all the database tables related to MPT fit in memory, the software overhead of NDBX associated with database read operations are actually pretty high, and we measure it to be around 1.2 microseconds per hour. So to make things even worse, now what if we can't fit the MPT in memory? We rerun the live sync experiment with also under different limits. So this table summarizes the result. It's easy to see that, first of all, the Merkelization cost far exceeds the other costs, for example, the execution cost and the data persistent cost. And second, when we go from 512 gigabytes to 8 gigabytes, the Merkelization has a slowdown of almost 7x, which results in an overall slowdown of about 5.3x. And the TPS number just drops from 1,000 to less than 200. Okay, now let's do a quick recap of our journey before getting into part 2. So we start with a nice juicy 14,000 TPS at the beginning with historical sync. Then we add Merkelization in live sync, and the throughput just dropped to 1,000. Furthermore, if we further limit the memory size to 8 gigabytes, we end up with 200 TPS. And if the full node operators are not comfortable spending all their CPU power just on block verification, we're only comfortable with, say, 10% CPU utilization, then maybe we're looking at just a miserable 20 TPS. And so you see there's a trend there, right? But fortunately, we can do much better. So at MegaETH, our belief is that L2 is actually the best place for performance innovation. Why? Because L2 enables the so-called heterogeneous scaling. That is, different types of nodes can vary significantly in their numbers and in their hardware requirements. For example, at L2, you only need a small number of sequencers, so you can afford to run them on very beefy machines. And if you're doing ZK rollups, then proven nodes will have to run on specialized hardwares anyway. And if you're doing OP rollup, and if you design your challenger node to be stateless, then their hardware requirements can be extremely low. And finally, for rollup full nodes, they actually don't need to re-execute transactions. So they can they can actually run on much cheaper machines. However, there could be hundreds of thousands of rollup full nodes if your rollup is very popular. Note that this basic idea of heterogeneous scaling was actually introduced long ago. For example, in 2021, in Vitalik's ambient post, it already explained the idea that if you want high performance, then it's inevitable that you will end up something with a relatively centralized block production design. However, it is acceptable if you can guarantee the block validation is still trustless and decentralized. And in addition, if you if you have some still have some censorship resistance protection mechanism. So let's just run L2 sequencers on Solana level hardwares. So that is a dozen CPU cores, at least 256 gigabytes memory, fast NVMe SSDs, and more than 1 gigabit per second network connection. We can also apply all the software tricks we know to improve the software efficiency. For example, for execution, we can do parallel AVM. We can exploit the parallelism both at the CPU level and the SSD levels. And then we can also do JIT compilation of EVM bytecode to native code, which allows us to boost the single thread performance of EVM. As for Merkelization, we can parallelize Merkle updates. REST doesn't do it yet, but it should be trivial to do it. And we could optimize the underlying database for the Merkelization process. We can even design much better data structures to replace the state trie, like to replace the ManPT or vertical tree. But sequencers are not really the problem. The real question here is whether full nodes can actually keep up with the beefy sequencers. Now, this is our full node. Maybe it has 4-core CPU, 8 gigabytes memory, and 100 megabits per second network connection. How can it keep up? So let's briefly walk through the workflow of a full node. First of all, L2 full nodes can rely on external proofs to check the check the correctness of state transition. So they don't have to re-execute the transactions themselves. They can just receive state diffs over the network advertised by the sequencer. So the nice thing about it is that the state diffs can be highly compressed, which helps save the precious network bandwidth of full nodes. And second, after receiving the state diffs, the full node needs to apply the state changes to their local databases. But fortunately, batch writes can be executed pretty efficiently, and the data locality also helps here. So hopefully, most of the updates will be absorbed at the cache layer of the database, reducing the disk item. Finally, the full node needs to update its state trie if it wants to serve like clients. So, and by the way, the state trie will be too large to fit in 8 gigabytes. So this is probably the most challenging part. However, we are pretty optimistic about it. We think it is actually very doable by combining a number of smart optimizations. So, well, this is our vision for future high-performance L2s, and we call them mega rollups. And sorry, I'm being a little bit sloppy in the use of terms here, so feel free to replace rollup with Validian, L2, Optimum, or any term as you see fit here. Our vision is that each mega rollup will be able to support 100 to 200,000 transactions per second in the future, and they can support very large state, like terabytes of state, without performance degradation. And there could be hundreds of thousands or thousands of them. Sequencers of mega rollup will be somehow decentralized. However, we don't want to reintroduce the network or consensus bottleneck. Mega rollup have to be built on a high bandwidth DA layers, such as EigenDA. And perhaps we also need a specialized and highly optimized settlement layer if Ethereum would become a bottleneck in the future. Okay, so this is all I have, and I'm happy to take any questions.